the function, the given function has isolated singularities at 6 root of -1 and analytic everywhere else. These roots are C6 exponential iota pi by 6 plus 2k pi over 6. K is varying from 0, 1, 2 up to 5. These are the 6 roots. 3 roots C0, which is e power iota pi by 6, C1, which is iota, C2, which is 5 iota pi by 6 e power this one. These lie inside the upper half plane inside C, given inside C, the upper half plane, for r greater than 1. I'm going to repeat a few steps again. Step 1 is that you have to make the integral. If the integral is from 0 to infinity, then you have to change that integral from minus infinity to infinity if the function is even. Step 2 is we change the function from real valued function to a complex valued function, so that for y is equal to 0, both f of z and f of x are equal. So we just replace x with z in the given function. Okay. Then instead of finding the value of the given integral from minus infinity to infinity, we will evaluate the contour integral f of z over the contour c, and the contour will be a semi circle in the upper half plane. Okay, and then fourth step, we will find the singularities of the new complex valued function, and then locate those singularities, how many of them are inside the contour and how many of them are outside the contour. Okay. So for the singularities inside the contour, we can see here that this contour integral is nothing but this is 2 pi I b1 naught plus b1 plus b2, where b naught, b1 and b2 are the residues. These are the residues. So we can evaluate this given integral C over the contour C by finding the residues, 3 residues, and adding them and multiplying it by 2 pi I. That will give us the value of this contour integral. So the next step is how we can associate given this this contour integral with the given real valued function. Okay. Residues of f of z at C0, C1 and C2. Now as a fifth step, we can write this contour integral f of z dz as where C, what is C? C is the combination of a line and the half circle. So we can write this integral over the line, that is minus r to r f of x dx, because on this line f of z and f of x both are equal, whereas over the contour CR it will remain f of z. This f of z here is replaced by f of x, because on that line both are equal. Okay, so whereas this is nothing but this is this one. Thus integral minus r to r f of x dx, and here that is equal to 2 pi I b0 plus b1 plus b2 minus integral CR f of z dz. This equal this one, and we have taken this on the other side. Okay. So, sorry, we have replaced this with this one, okay, and then after replacing we have taken this on the other side. This is on the left hand side, this is on the left hand side, and we have taken this on the right hand side with the negative sign. This is, what is this? This plus this one. So we have replaced this plus this, putting here. This is same. This is same as this one. This plus this one. Understand my point or not? So when we take the limit over here, you know, this term is known to us now. We can find the residue for the given function. We can sum of them. The only thing is that when we take the limit r tends to infinity, this will give us the principal value of the given function. And we have to prove that when r tends to infinity, this becomes 0. If this becomes 0, then it is just the value of this, just the residues over here, sum of the residues times 2 pi I. This will give us the principal value. For only when this tends to infinity. So the point here is that we have to prove when r tends to infinity, this becomes 0. Okay. This is step 6. We take the limit r tends to infinity, integral minus r to r, and f of x is now given to be this one, dx is, there is no effect of limit over here, it is just 2 pi I because it is a constant, minus limit r tends to infinity, integral over CR f of z dz, which is z square over z6 plus 1 dz. Okay. Now this is nothing but this is the principal value that is to be determined, and this can be determined with the help of residues here, provided this tends to 0. If this contributes something, then it will make change over here. If it does not contribute anything over here, it is just the value of the residues over here. Okay. So as a next step, we have to prove.
Step point. इसमें जो हमने इंटीग्रेशन की है माइनस आर को हमने फंक्शन लिया है एफ ऑफ एक्स और दूसरे के लिए हमने फंक्शन लिया है एफ ऑफ जेड.
Because what is the contour? Look at the contour. The contour is something like this. This is minus r, this is r. This whole is closed contour is C1. This contains two parts, L and CR. Okay. Along this line, what is y? Y is 0. So along this line, f of z is equal to f of x. No need of writing here f of z. Although, for your satisfaction, first write f of z, then putting y is equal to 0 for this only, you can get this f of. But for this purpose, because we are dealing with the complex plane, for the points here, this is not equal to f of x. This will remain f of z. Understand? And then after making use of these two equations, we arrived at this. Okay. Now, as is step 6, what we have done, we have taken the limit of this whole equation. Now, step 7 is we will prove that limit r tends to infinity integral over CR dz is equal to 0. This part is 0. Okay. So the final will remain over here. So how we prove? In the chapter on integrals, we have discussed certain integrals. Those integrals can be evaluated without finding the value of the integral. Using that method, we can prove here that because we are given z mod is C. What is CR? CR is z mod is r, and this r is greater than 1. This r is greater than 1. Thus, z mod square is equal to r square, and z6 plus 1 mod, it is greater than or equal to z6 mod minus 1, or it is r6 minus 1. So that this 1 over z6 plus 1 whole mod is less than or equal to 1 over r6 minus 1. Okay. Thus, integral over CR z square over z6 plus 1 dz mod is less than or equal to integral over CR mod of z square over z square plus z6 plus 1 dz, and it is nothing but it is mr into L. Now this L is different from that L. This L is the length of the semicircle that you may